Hello everyone, my name is Ryan. I'm going into my fourth year of mechanical engineering undergrad at UCSB. So here I have a FE prep question for you guys. It says the heat flux through 1 meter squared of the steel aluminum plate system shown is most nearly what? So it is asking us what is the heat flux through this system we have here. And here I have a diagram to show you guys exactly what is happening here. So we have our steam here, and this side is our environment right here. And what happens is, so there's a temperature Ti from the steam, which is 544 K, and does a convective heat transfer to the surface of the carbon steel, and we will label that as T1. Now, through this carbon steel, a conductive heat transfer is happening. So we went from convective here to conductive. And from T1 to T2, that's conductive. From T2 to T3 is also conductive because the heat is traveling inside an object. And once it reaches T3 to T infinity, the environment, that goes back to convective. So to do a problem like this that tries to find the heat flux through objects or stuff like that, where there's a combination of convective heat transfer, conductive heat transfer, or radiative heat transfer, you want to always think about doing a thermal resistance network. Before we do that, I just want to write down the equations that we're going to use for the thermal resistance of convective and conductive heat transfer. So for our conductive heat transfer, I'm going to say R CONV. The equation for that is 1 over the heat transfer coefficient multiplied by the surface area. So that is the thermal resistance of convective heat transfer. For conductive heat transfer is very similar, but it's different. It's the length over the thermal conductivity K times the area, cross-sectional area. Okay, so now once we have our equations, I'm gonna start writing our thermal resistance network. So we go from T1 all the way to T infinity, and we do not miss a step. T1, our heat goes from T1 to our heat goes from Ti to T1 to T2, T3, and finally T infinity. So, and this is our resistance. And we do this because to solve a problem like this, it is actually very analogous to electrical circuits resistance network. So we can use that to solve this question. And to make it more clear, I'm going to write down the resistances from each temperature to the next temperature. So from Ti to T1, that's convective, which is going to be 1 over H bar, which is our heat transfer coefficient, and it is H bar initial, as we can see from the system above, and T1 to T2, that's obviously going to be conductive, as we've said before, LS, the length, over K times A. Also here it's times the surface area. Okay, so for T2 to T3, it's also conductive, but we have a different length, which turns out to be the same length anyway. So I just want to be sure here that I'm labeling this correct. This is Ks, which is the thermal conductivity of the carbon steel, Ka for aluminum, and A for the cross-sectional area. So next, and the last one is another convective heat transfer, H bar infinity times surface area. Okay, so one thing you'll note here is that we actually don't need to care about area for now, because the area, the surface area that, and the cross-sectional area that the heat is traveling through is the same. So to solve this question, I have another very important formula, which is the heat flux equals Q over A. And through the through derivations, this would actually be equal to delta T times A over R total. And R total is just the total resistance. So that would mean all of this add up to each other. This is R total. So let's just plug in our knowns. So we have Q, that's what we're trying to find, equals delta T, that's 554 Kelvin, and you want to do this in Kelvin. But it actually doesn't really matter if we do it in Kelvin or Celsius, because it all cancels out. Our area, we don't really need to care about that for now. And I'll show you why later on. So this is our delta T times A, and our R total, which is basically the sum of all our resistances. I'll just write out our knowns now. HI is 700 plus times the surface area, plus LS, which is 0.01 meters. So it's 10 millimeters, and we're making it 0.0. We're changing it to meters. Over our thermal conductivity for carbon steel, which is 60, times our cross-sectional area, plus another 0.01 length for the aluminum, over 240 for thermal conductivity of aluminum, times area, plus 1 over, finally the last mode of heat transfer, 100 for heat transfer coefficient for the environment, times the surface area. So one thing you'll notice here, and in most thermal conductivity questions, the areas are the same. The cross-sectional area and surface area is the same. So what you could actually do is just cancel all of the areas out, and you won't even need to know the area. So what remains from our equation is simply 544K minus 300K Kelvin, 1 over 700 plus 0.01 meters over 60 plus 0.01 over 240 plus 1 over 100. Okay, so solving for that, we get a value of 20,968 watts per meter squared. And this is our Q. This is what we want. So let's look at the options, and it is not one of the options, unfortunately, but with the FE exam, they want you to pick the closest one. So the closest one would be C. Please comment down below if you have any questions, and I'll try to answer them. Hope this was very clear. Thank you.